Okay, let's take a look at a few examples of rationalizing denominators. In other words, taking a fraction, some sort of rational expression, and rewriting it in such a way so that the denominator has no radicals in it, nor rational exponents, because that's really the same thing in disguise. Let's start with an easy one. Example number 1. Suppose we wanted to rationalize 3 over the square root of 28. Okay. Well, the first thing you might realize is the square root of 28 is not in simplest form. 28, of course, is 4 times 7. 4 is a perfect square, so we know we can pull that out. We could rewrite this as 3 over the square root of that 4, again, pulling it out as a 2, times the square root of 7. So that's 3 over 2 radical 7. Okay. Of course, the trick here is to rewrite this in a way so this radical 7 does not show up in the denominator. Now, if we were only taking the square root of 7 squared instead, that'd be great, right? Because then that 2 would just be a 7 and the radical would be gone. Well, let's make that happen. If we want to see the square root of 7 squared here, we need another square root of 7 in the denominator. Put one in. Of course, we can't just do that willy-nilly. That would change the expression. But if we multiplied by square root of 7 over square root of 7, that would have the right effect, right? We would get another square root of 7 in the denominator. Granted, we pick one up in the numerator. But we would have really just multiplied by a well-chosen value of 1. And that doesn't change the value of this whole expression. So we put in what we wanted, and we compensated for the insertion. Now what do we have? 3 times the square root of 7 up top, and then 2 times the square root of 7 times another square root of 7. That's 7 there times 2. That's 14, and the radical is gone from the denominator. That's our rationalized expression. Let's look at another one. Example 2. What if we wanted to rationalize the denominator for 5 over the cube root of 4? Okay, now let's see here. 4, of course, is 2 squared. Always good to factor what's inside the radical first. See what you have to deal with. If only we had 2 cubed there, this would be easy, right? The cube root, which is the thing we're trying to get rid of, and the denominator, the cube root of 2 cubed would just be 2. That'd be wonderful. But we're missing a single 2 inside that radical, right? Well, let's insert one. Let's multiply this by the cube root of a single 2. Of course, those would combine together to give you cube root of 2 cubed, which is exactly what we want. Then the radical could go away. But I can't just multiply the denominator by something. That would change the overall value of things. So just like before, let's multiply by a well-chosen value of 1. Let's insert this cube root of 2 and compensate for that insertion by also multiplying by cube root of 2 in the numerator. So we have really just multiplied by, again, a well-chosen value of 1, which is not going to alter the expression's value at all. So now, what do we have? 5 times the cube root of 2 on the top over the cube root of 2 squared times 2. That's 2 cubed. That bottom, of course, is just 2. So we have 5 times the cube root of 2 over 2. There's no radical or rational exponents in the denominator here. We are done. Okay? Let's do one more. Example 3. 4 times the square root of x over 2 times the square root of x plus 1. What can we do here? Again, we're trying to rationalize the denominator. That means we want to get rid of this radical. But how can I do that? Can I multiply this denominator by something to make that happen like we did in the previous 2 examples? What could we multiply by? If I multiply by the square root of x, like this, That's not going to help. The square root of x times square root of x, that'll get rid of the radical there, but the square root of x times 1 just reintroduces a square root. So we don't want to do that. So what can we multiply by? Do you remember when we were looking at factoring things, one product in particular, a plus b times a minus b, was of interest. That gave us a squared minus b squared. So whenever we saw a difference of squares, we could break it into something like this. But let's consider this in this direction now. If you started with an a plus b and you multiplied it by a minus b, you get an expression where the first term has been squared and the second term has been squared as well. If that first term was a radical, or the second term was a radical, or even both of them was a radical, they would now be gone upon multiplication by a minus b. So what I would like to do back here is multiply this by 2 square root of x minus 1, the so-called conjugate of this denominator. As before, though, if you multiply by something here in the denominator, we need to go ahead and compensate for that by multiplying as well in the numerator by that value. So here again, we just really have a well-chosen value of 1 that we're multiplying by, and it's not affecting the overall expression at all. Let's crank it out. So we have 4 root x times this quantity, 2 root x minus 1, all of that sitting over a plus b times a minus b. This is a difference of squares. Square the first thing, that's 4x, right? 2 squared times x. Square the second thing, that's a 1. And then, of course, we have a difference here, right? That's just using this special product rule. Okay? If you want, you can distribute that top 4 root of x, if that's necessary. 4 times 2 would be 8. Root x times root x is a single x. And then, of course, minus 1 times that. That'd be minus 4 root x on the top. Either one of these is really probably fine. In most contexts, you'll actually stop here because having the factorization of the numerator will be advantageous. I'll go ahead and circle this as the final answer. And again, notice the radical is gone in the denominator. Okay, so we're using that special product rule from factoring to rationalize a denominator. Okay?